Welcome everybody to Algebra 2, Section 2.2, Linear Functions, Part 1. We're talking about standard form, slope-intercept form, and graphing today, especially using x and y intercepts as well as slope-intercept form. So let's talk about linear relations first. Linear relations, we know functions are a more specific type of relations from 2.1. So when points lie on a graph along a straight line, it's called a linear relation. They are related to each other. Now, linear relations can be represented by an equation. For example, the equation of this graph is x plus y equals 8, or there's other ways to write it as well. So these linear relations, we're also going to call them just linear equations, basically from here on out, stating that they are equations, or that we can also call them linear functions, if you will. I'll spoil it by saying they are, in fact, functions. It would pass the vertical line test, for example. They can be written in standard form. And standard form is ax plus by equals c, noting that a, b, and c are capital letters. And a, b, and c are integers, which means they're non-decimals, non-fractions. And a has to be greater than or equal to 1, aka it must be positive. And the GCF, or greatest common factor, of a, b, and c is 1, meaning that if something divides into each of them, we need to divide it to reduce it. So we're going to take these and write them each in standard form. So once again, we need to meet three criteria that, or a few criteria, I should say. We really have 4 criteria. That a and b are on the left-hand side, so x and y are on the left-hand side. That we have no decimals, no fractions. That's our second criteria. Our third criteria is that the number with x must be positive, and our fourth criteria is that their GCF must be 1. So here on number 1, we note that x and y are on the left, so we don't have to bother moving them. We have our x, y on the left, our constant on the right. Our GCF of these three numbers is 1, and there's no decimals or fractions to worry about. So we just have to make this a positive number. How we do that is we're going to multiply by -1, or divide by -1. And if you multiply one side by -1, you have to do it to absolutely everything. So -1 times 5x is positive 5x, -1 times 6y is -6y, and -1 times -12 is positive 12. So we're okay with the fact that this y became negative in the process. We're only concerned that the ax is positive. So now the ax is positive, the x and y are on the left, while c is on the right. We have no decimals and no fractions, and the greatest common factor of 5, 6, and 12 is 1. Now, if this was like a 3x, now the greatest common factor is 3, and we have to handle that separately, which we'll see in example 3. But for now, we know the GCF is 1, and we're good to go. Number 2, y equals 2x minus 9. So we have our variables on two different sides, so I need to move this variable over here, so that way my variables are on the left and my numbers are on the right. So I subtract 2x from each side. I can't combine 2x and y, so I just write -2x plus y equals -9. And we do like the x to be written before the y to keep it alphabetical. Now, I don't have any decimals or fractions. My variables are on the left. I have a common denominator between 2, 1, and 9. Not a common denominator, but a common factor, a greatest common factor of 1. But this is negative. So to fix that, we multiply by -1 to absolutely everything. So we get positive 2x minus y equals positive 9. Once again, we're completely okay with the fact that this by is negative. What we're concerned about is the ax being positive. Number 3 here, we have our variables on the left, but we also have this number or constant on the left. So we have to move that by adding 24, giving us 9x plus 6y equals 24. So now our variables are on the left. Our a is positive this time. We have no decimals or fractions. However, we have a greatest common factor higher than 1. 9, 6, and 24 all have the common factor of 3, meaning we need to divide every single thing by that greatest common factor and make this 3x plus 2y equals 8. And that would be our answer now. Number 4 here, I need my variables on the same side, so I'm going to add 7x to both sides to move it away from my number and toward my variable, and get 7x plus 7y equals 7. Now, we have no decimals, no fractions. Our AX is positive, the variable's on the left, but the last item on our checklist is that the GCF here is not 1, it is 7. So we divide everything by 7, and we get x plus y equals 1. And now the GCF is 1, so it meets all 4 criteria. The 4 criteria being variables on your left, being criteria 1, criteria 2, no decimals, no fractions, criteria 3, AX is positive, and criteria 4, a GCF of 1. Those criteria come in no particular order, just 4 criteria for us to follow. Number 5, we got some fractions here, okay? Our AX is positive, our variables are on the left, our numbers on the right. So now to get rid of these fractions, what we do is we're going to multiply again. Fractions are division. To undo that division, we'll multiply. So the question becomes, what in the world could we multiply to get rid of these fractions? Well, to get rid of this fraction, if we multiplied by 4 or 4 over 1, those would reduce. However, we don't just need to get rid of that fraction, we need to get rid of this too. And 4 times negative 1/3 would not get rid of the fraction. Well, to get rid of that fraction, if we multiplied by 3 over 1, that would get rid of that fraction. But 3 over 1 would not get rid of this fraction. So we need a number that would get rid of both. And so we need to find the least common multiple of those two, the lowest number that 3 and 4 both multiply up to. And that number would be 12. So we're going to multiply this by 12, or 12 over 1, on both sides. It might not be a bad idea to do this work off to the side as we do 12 times 3 over 4x. So 12 over 1 times 3 over 4x. Look to reduce. 12 and 4 become 1, and try that again, not 1, but 3 and 1. And multiplying straight across gives us 9x. So I'm going to have 9x here. 12 over 1 times negative 1/3. Y. Reduce 12 and 3 by 3 to become 1, and try that again, 4 and 1. And we get negative 4y. Multiply the other side by 12 and get 12. And now the variables are on the left, there's no decimals or fractions, the AX is positive, and the GCF of 9, 4, and 12 is 1. Number 6, we have variables on split sides. So I'm going to move my y over here by subtracting it and getting 16x minus y equals negative 2. If you took care of the fraction before this step, that's fine. Now my AX is positive, so I don't have to worry about multiplying by a negative number, but I do have to get rid of this fraction. And I only have one fraction to worry about, so I'm going to multiply by 6 over 1, the denominator over 1. Not necessarily the reciprocal, but the denominator over 1. So here, for example, I didn't do 12 over 3, I did 12 over 1. So here, those 6 times negative 1 times 16x creates just being x, the 6 and 6 reduce. 6 times negative y is negative 6y, and 6 times negative 2 is negative 12. So our variables are on the left. We have no decimals or fractions. Our AX is positive, and our greatest common factor is 1. Moving on to talk about slope-intercept form. Slope-intercept form, linear equations are often written in this form. They're most often written in this form. And it's y equals mx plus b, or you can think of it as f of x equals mx plus b, remembering that y is the same thing as f of x. Now m we know as the slope, and b is what we call the y-intercept. The intercept is where it crosses the axis, so the y-intercept is where it crosses the x-axis. Later in this lesson, we'll be talking about the x-axis, which is where it crosses the or the x-intercept, which is where it crosses the x-axis. Let's talk about slope a little bit more in depth. Slope is the constant rate of change between points. So a good way to think about it is rise over run, or our formula for slope, which will cover next lesson. Sorry, I had to look ahead in the notes to make sure when we were covering it. My apologies for that. Our formula for slope will be covered next lesson. But for now, think of it as a rise or run, how far it's going up and down compared to how far it's going left and right as a fraction. And there are 4 types of slopes. We're going to sketch them down below. So the first type is a positive slope. So that fraction could be positive. And if that fraction is positive, it'll be some line that is going uphill when you look at it from the left to right. So as we go from the left to the right, it's going up in some manner. Now maybe it's going up less steeply, or maybe it's going up really steeply. But regardless, it's going up from left to right. Our next type is negative slope. So maybe the fraction is negative. This will be going downhill from left to right. So from left to right, negative slopes will going downhill. Once again, maybe it's really steep downhill, or maybe it's a very gradual downhill, or somewhere in between. But regardless, it'll be going downhill from left to right. Our third scenario is that the slope is equal to 0. So we have positive numbers, we have negative numbers, we have 0, which is neither. And this would be my iPad glitched on me there, a horizontal line, a perfectly horizontal line. So this horizontal line, a good way to think of it is that as it's rising and running, it's not rising any between these points. It's not going up or down, but it is going left and right. So when we think of this rise over run as a fraction, rise over run, this would be 0 divided by any other number, because it's 0 up and down for rise, but there is a number as it moves left and right, and that would just equal 0. So you can think of it as the rise is 0. And another helpful trick here that I learned from a student years ago is that you can remember horizontal lines have a slope of 0 because you can make the letter Z out of it for 0. And our fourth and final slope type is undefined. So a fraction can be 4 things. A fraction can be positive, negative, 0, or undefined. How that would happen via the math would be once again talking about rise over run. And undefined is when you take any number divided by 0, including 0 divided by 0. So any number divided by 0 is undefined. We cannot say what happens. We should abbreviate to U and D a lot because you can't divide by 0. It breaks math. And so we have our little cop-out saying undefined. We can't define it. And how this looks here when the run is equal to 0 is it looks like a vertical line. Just a vertical line, perfectly straight up and down. And we can see on this line that it is rising, but it's never moving left and right, aka running. A good way to remember this is that you can make a U for undefined, similar to how you can make a Z for 0 for the horizontal line. On to this next page here, we're going to be graphing these. So it's a good idea to write it in the slope-intercept form before graphing. That's often how we prefer it. Here on number 7, it's already written in that form. So when it's written in this form, once again, y equals mx plus b, we can know instantly the m is 2/5 because it's multiplying with x, and the b is 7 since it's adding at the end. Now how we go about graphing this is we begin with the b, is how I like to say it. Getting a little bit cheesy there with that alliteration. And so as we begin with b, we remember that's the y-intercept. So it goes on the y-axis. So you count up 7, and you go there on the y-axis and make your first dot. Now, you need more than one dot or point in order to have a line, and so I'm going to have it go with the slope up 2 over 5. Or it can also go down 2 over 5. The important part is since this is a positive fraction, it'll go uphill in some manner. So if I go up 2 and over 5, I kind of run off the graph pretty fast. So I can go down 2 and left 5. And now from left to right, these are still going uphill. So as long as I make sure it's going uphill still, since it's positive, I can go down and left or up and right to make new points with my slope. And I can continue making points with my slope, but I do run out of the graph pretty quickly. And then you just connect them, and we have arrows on each end. If you do not have the arrows, it would actually be wrong, because those arrows tell us it keeps going forever, but we just stopped drawing at a certain point. Number 8, f of x equals negative x plus 2. So this is in slope-intercept form. The m is whatever number is multiplying with x. That's secretly negative 1. The b is whatever is being added or subtracted at the end, and it's positive 2. Here, we need a fraction for our m, because it's rise over run. So the rise over run, the negative 1, is secretly divided by 1. So we begin at b again by going up 2. And then we need more points by going up 1 and over 1, or down 1 and over 1. A rise of negative 1 and a run of 1. Regardless of whether we think about the negative being on the top of this fraction, or the bottom of the fraction, or out in front, which I think is the most helpful way to think about it, is out in front here. The fraction as a whole is negative. So the rise is 1, the run is 1, and we're going downhill from left to right in some manner. So I'm going to go down 1 and right 1, or up 1 and left 1. I encourage you to go at least 1 point in each direction when you can, which we can here. We have plenty of room to do so since the points are so close together. Whereas on number 7, we didn't have much room to do so. And we connect those lines and draw an arrow. Number 9 here, we might think m is 1, but that'd be wrong because it is not in slope-intercept form, so we can't identify the m yet. We need to get it in the slope-intercept form. Quick reminder that slope-intercept form written above is y equals mx plus b, aka the equation is solved for y to be by itself. So we have to get y by itself by getting rid of everything else around it. So I will start by subtracting x from both sides. I get 3y equals, I want to write the one with the variable before the one without the variable. Remembering it goes mx first. So negative x plus a negative 15, or just minus 15. Now I have to divide by 3 to continue getting y by itself. Y equals negative 1/3. There's secretly a 1 there. X, whether you write the x on top of the fraction or off to the side, it's the same thing. If it's off to the side, it's secretly x over 1, which would multiply straight across to become x over 3, or 1x over 3, minus 5. And so now I have my m, or my slope, is 1/3, my b, negative 1/3, and my b is negative 5. So I begin with b, and I go down 5, make a point, and to make more points I use my slope, knowing that negative will be going downhill in this fashion. So if I'm going up, I'm going to the left, or if I'm going down, I'm going to the right. So the rise is 1, the run is 3, so up 1 over 3 to the left, or down 1, 3 to the right. Like I mentioned, I like to make 1 point in each direction at least, and then connect them with a line. Draw arrows on the end, and we're good to go. Number 10 here, once again, not in slope-intercept form. So we could either move both of these to the other side, or we could just move the y to the other side and then make it positive by dividing by negative 1. Let's say I go ahead and subtract 4x from both sides, and at the same time I'm going to go ahead and add 1 to both sides. I will have y equals negative 4x plus 1. Congrats, y is by itself. So now I can know that my m is negative 4, and my b is 1. Negative 4 is secretly divided by 1, which will help me with the rise over run. So b is 1, so I begin there. Let me try doing that point again. And then my slope is negative, so I'm going to go downhill from left to right. And I'm going to go down 4, 1 to the right, or up 4, and 1 to the left. And connect these points with a straight line and an arrow. Now, if your line curves a little bit like some of mine did earlier, for example, like this isn't the most perfectly straight line you've ever seen in your life, that's okay. I don't want it to be so wobbly that you can't tell what's going on, but as long as it's decently straight, I'm good with it. Vertical and horizontal lines. As I mentioned before last lesson, I mentioned how when we have x equals a number or y equals a number that has vertical and horizontal lines. So when you see one of those, a vertical or horizontal, it's either x equals a number and y equals a number. And how we can remember that is here, this vertical line, the x value is never changing. The x here is -3. X is -3 at every single point on this graph. And so since x is -3 everywhere on the graph, the equation is x equals -3. The slope of this line is undefined, reminding us that we can use the u there. This other line, horizontal lines, will always be in the form y equals a number, because the y value is consistently the same number the whole way across. The y value is consistently here 1. And you can always make a z out of this to remember that the slope is 0, which is why it's y equals 0x plus 1, but 0 times x is 0, meaning we just do 0 plus 1, getting us back to y equals 1 as our answer. Parallel and perpendicular lines. So parallel lines are lines that never, ever, 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 ever touch or intersect, and the slopes of those are equal or the same. However you want to word that, equal or the same. I'll write both down. Whereas the slopes of perpendicular lines are very much not that. They are opposites, which means that they are opposite signs as far as positive and negatives go. And they are reciprocals, which means that you flip them. Now, if there's 3 scenarios for slopes, for any 2 slopes, either those slopes are the same or they're different in any way. Let me clarify that. There's 2 scenarios. Either they're the same or they're different. Now, if they're different, they might be perpendicular. They're only perpendicular if they're different in this very special and unique way, or they're opposite reciprocals of each other. If they're different any other way than being both opposite and reciprocals, then they are not perpendicular, nor are they parallel. The majority of 2 lines that we see are not either parallel nor perpendicular, but we do have lines that are both parallel and are both perpendicular. So to determine whether this pair of lines is parallel, perpendicular, or neither, we have to find their slopes and determine if they're the same for parallel, opposite reciprocals for perpendicular, and literally any other combination for neither. So finding the slopes on number 13, we solve each of these for y, and if we solve for y, we'll know the slope is whatever's with x, because that would give us slope-intercept form. When it's in this form, we can find the slope quite easily. So to get this left equation in y equals mx plus b, your slope-intercept form, I'll subtract 10x and get 5y equals -10x plus 5. Then dividing every single thing by 5 results in, I should say, y equals -2x plus 1, where I can identify m as -2. My other equation, I have to move these around, so I'm just going to move my 16 toward my x and also flip my equation around. So I'm going to subtract 16 from both sides, and I'm going to flip my equation around. So instead of it being 2y on the right hand side, I'm going to flip it to 2y on the left hand side. Instead of this -x over here, I'm going to move it over here. And subtracting 16 results in this. The in-between step I didn't show is this, where I just rewrite 2y plus 16 equals -x. And I did no math except for flip the equation around. So the left is the right and the right's the left. And then I subtracted 16 on both sides from there. Now to get y by itself, I divide by 2. Y equals -1/2 minus 8. So here the slope is -1/2. Now, these numbers are reciprocals of each other. -2 is secretly over 1, and 2 over 1 and 1 over 2 are reciprocals. However, they are the same sign. So in order to be perpendicular, they have to be opposite signs and reciprocals. So these are neither. they'll intersect in some non-special way. Number 14, doing the exact same thing here. I'm going to go ahead and try and get this negative 6y, or the y by itself, by subtracting 8x first and getting negative 6y equals negative 8x plus 42. Dividing every single thing by negative 6 results in y equals 4/3 x minus 7. We do want to keep our slope as a fraction, an improper fraction, rather than decimals or mixed numbers. The reason why we like improper fractions for slope is it's easier to graph the rise over run this way. So we know that the slope here is 4/3. This other one, all we have to do is divide by negative 3. And y equals negative 3 plus 4/3 x. Negative divided by negative is a positive there. And even though it's written out of order, which is not how it should be, we can still see the m is 4/3 because that's the number multiplying with x. And we notice these are exactly identical with each other, meaning those two lines are parallel. Now, an abbreviation or a symbol meaning parallel would be 2 slashes, which look like 2 parallel lines. So oftentimes, instead of writing out the word parallel, I'll do that symbol instead, which once again just means 2 parallel lines. You'll often sometimes see the symbol as just 2 straight up lines, but I don't like that as much because it looks like the number 11. It also looks like absolute value bars or 2 L's. It gets very confusing, whereas 2 slashes is unique in math. Number 15, working on getting this left equation in slope-intercept form by adding 8x, we get 8y equals 8x, with 0 being that y-intercept here so far. And dividing by 8 on both sides, absolutely everything, gives us y equals x. And so the slope here is 1, or 1 over 1. And it's secretly plus 0, even if we're not concerned about the y-intercept for this problem set. In the other one, we are subtracting x to start, or adding y to start. You pick. I'll subtract x here, and get negative y equals negative x plus 4. Then dividing everything by negative 1 gives us y equals 1x, or just x, minus 4. So here, the slope is 1, or 1 over 1. Those are again identical, meaning these lines are parallel. You can either write out the word, or do that little symbol, or do an abbreviation, PAR, period. Number 16, x equals 2 and y equals 2. Well, we covered before that x equals 2 is a vertical line with a slope that is undefined. And y equals 2 is a horizontal line. Y equals numbers is always horizontal, and this slope is 0. Now, any vertical line with any horizontal line will 100% of the time be perpendicular, because these make right angles. Mathematically, we could also know they're perpendicular, because as we discussed on the last page when we talked about slope, is that the slope for undefined is some number divided by 0, and the slope for 0 is 0 divided by some number. And those are reciprocals of each other, and 0 can't be positive nor negative, and so they're as close to opposites as 0 can get, meaning these are, for our concern, opposite reciprocals of each other. So they are perpendicular. But you could write out the word perpendicular, or you can do this little upside down T, which looks like mini perpendicular lines, especially if I add on this bottom part. But if I add on the bottom part, it also looks like a plus sign. So I leave that off and make a unique symbol for math. And once again, you could also write perpendicular down. I lost a C there. Or abbreviate perpendicular to PERP. Next up, let's find x and y intercepts, and then we'll use them to graph. So we talked about this earlier. This idea of x-intercept is where it crosses the x-axis, and the y-intercept is where it crosses the y-axis. So to identify it for this graph on the right, the x-intercept, which I'll abbreviate as x-int, is right here, -3, 0. And the y-intercept is, as we'll identify on the graph, I like to do colons there, 0, 4. Now, I said I like to do colons here after y-intercept and x-intercept before the parentheses or the point. You don't have to do a colon there. You could just do like a period to show that you ended the abbreviation of y-intercept or x-intercept. Now, we notice for these that for x-intercept, the y value is 0, because in order for it to cross this line, the y value must be 0. The y value can't be like 2 when it crossed that line. The y value can't be -5 when it crossed that line. The y value has to be 0 in order for it to cross that line. So 100% of the time, the y value will be 0 for an x-intercept. Similarly, the y-intercept has a 0 for the x value, because 100% of the time, in order for it to cross this y-axis, it must be 0 left to right. The x value must be 0. It can't be -2 and cross that line. It can't be +1 and cross that line. It has to be 0 exactly. The x-intercept is also referred to as a root, 0, or solution to the equation. We're going to get into that more in depth when we handle quadratics, but for now, just go ahead and write it down and know that we'll be calling x-intercepts by other names as we continue, calling them roots, zeros, and solutions. Now, to find these intercepts algebraically, I mentioned that the x-intercept always has a y value of 0, and the y-intercept always has an x value of 0, aka the opposite variable is always 0. So we can use this to our advantage, and we say when we find the x-intercept, we're going to set y equal to 0 and solve. And to find the y-intercept, we set x equal to 0 to solve, aka the opposite variable. And once you have those 2 points, you can graph those points and connect them to make your line. So to find the x-intercepts of this equation, or the x and y-intercept, the x-intercept, we would replace y with 0, and everything else stays the same. And now we solve for x. So we subtract 5 from each side and get -5 equals -2x. You also could have added 2x to both sides and kept these numbers both positive. Dividing by -2 results in a negative divided by negative or a positive, and we get 2.5 or 2.5 or 5/2. Now, while I prefer improper fractions for slope, and we always want those for slope, I should say, not just I prefer, I do prefer decimals for points that I'm graphing. Okay, so for points, I want decimals because it's easier to know where to graph 2.5 than it is to graph 5/2. Now this is the ordered pair, 2.5, 0, because we said the y was 0, and for x-intercepts, y is always 0. For the y-intercept, we make x 0. And that would be y equals -2 times 0 plus 5. So here, I do -2 times 0 is 0, and y just equals 5, because I don't need to write 0 plus 5, I can just write 5. And so that's the ordered pair, 0, 5, the x value being 0, the y value being 5. And now we found our x-intercept and our y-intercept. Now, some of us may have noticed that since this is in slope-intercept form, or y equals mx plus b, that this b over here, this 5, is the y-intercept. We already classified it as a y-intercept, and we used that to graph earlier. So if it's written in slope-intercept form, and you realize that, you don't even have to do all this work to find the y-intercept. You only need to do the work to find the x-intercept, because the y-intercept is already there, and we know the x value would be 0 as we see here. So we're going to find the x and y-intercept of these equations below, then we're going to graph using those intercepts. So on number 1, it's in slope-intercept form again, so I will know the y-intercept already. I can find it algebraically if I want still, but I already know it's going to be -1. So spoiler alert, y-intercept is already y equals -1, aka 0, -1. Because once again, y equals mx plus b, where the b is the y-intercept. To find the x-intercept, I need to plug 0 in for y, the opposite variable, and start solving for x. Adding 1 to both sides gets 1 equals 5x, and dividing by 5 gets me 1/5, or 0.2 equals x. That's the 0.2, 0, the y value is 0. So I found these intercepts, and now I'm going to go ahead and graph using them. So I plot these 2 points, point 2, comma 0, and 0, comma negative 1, and I'm going to go ahead and connect them, and I have my graph. Once again, I could have found the y-intercept algebraically here on number 1, and how you would have done that is I would have replaced 5x with 5 times 0. X becomes 0. And I start solving here, and I get 5 times 0 is 0, minus 1, which is just negative 1, which I already mentioned that it was. Number 2, once again, we know the y-intercept right off the bat since it's in y equals mx plus b form. So the y-intercept, which I'm going to label that way I know what work I'm doing, is y equals 2, aka 0, comma 2. The x-intercept, which once again I'm going to label the work I'm doing so I can follow along with it, would be y equals negative 6 over 5 times 0. I did that wrong, my apologies. I was replacing the x with 0. I need to replace the y with 0. So 0 equals negative 6 over 5x plus 2. I'm going to go and add 6 over 5x to both sides, so that way I just keep the numbers positive here. I could have subtracted 2 and that'd be fine as well. So now I need to get rid of this fraction multiplying with x, so oftentimes we think of dividing, but dividing by a fraction is messy, so we multiply by the reciprocal instead. 5 over 6 on both sides. On the left, everything reduces down to just x. On the right, I'm going to put this 2 over 1 and look to reduce. 2 and 6 reduce to 1 and 3. And multiplying straight across just leaves us with 5 over 3, or the decimal 1.6 repeating, comma 0. So I found my x and y intercept, and I'm going to go ahead and graph these two. So 1.6, comma 0, and 0, comma 2, and connect them. And I have my graph. So our last page here has 5 more examples for us to work through, where number 3 is still in slope-intercept form, but 4 through 9 or 4 through 7 are not. So on number 3 is my last opportunity knowing the y-intercept without having to do any actual math to get there. And that's y equals 16 over 3, which I'm going to call 5.3 repeating. And that's 0, comma 5.3 repeating. Once again, you can leave it as a fraction, improper, or mixed number, but I find decimals are easiest to graph as points. And so now finding the x-intercept, I make the y value 0, and I solve for x. So I add 3x to both sides just to keep it positive. Subtracting 16 over 3 would have been fine as well. Then I have to divide by 3. But wait a second, double-decker fraction, how do I handle that? So I put this 3 over 1, and now I can just multiply by the reciprocal like I would have on the last problem. 3's reduce, and I get x just like I wanted. I multiply the other side by 1 over 3, and 3 and 16 don't reduce, so multiplying straight across gives me 16 over 9. 16 over 9 would be as a decimal, 1.7 repeating. So that's 1.7 repeating, comma 0. And it is okay to round on that part when you're going to graph it, if you need to. Here we don't need to, obviously, because it repeats. So 1.7, comma 0 would be approximately there. I'm not going to take out a ruler and measure that you're exactly 0.7 repeating across, but if it's close, I'll give it to you. And 5.3 repeating would be 5 and 1/3 up, which once again, I'm not taking out a ruler and measuring that you're exactly 1/3 of the way up. Connect those two, and boom, we have our graph. Number 4, 4x minus y equals 8. So I'm going to go ahead and start finding the x-intercept first. I could find either one first, it really doesn't matter. So I make y 0. I notice here, 4x minus 0, I don't really need to write that, so I could do 4x equals 8. And then I divide both sides by 4, and I get x equals 2, which is 2, comma 0. Now, if you notice, up in this step here, since we don't really need that 0, I could go ahead and start dividing up here and kind of skip the orange step where I rewrite it. And I'm going to start doing that moving on here after this problem here. So that way we can save that step. But if you still need to write that orange step in, feel free. For the y-intercept, I'm going to rewrite it where x is 0. And so doing so gives us 0 minus y equals 8. Once again, you don't really need this step here, but you can if you want it. If it helps you organize, then please write it. To get rid of this negative with the y, because the negative still is with the y, we divide by -1 or multiply by -1 on both sides, giving us y equals -8, or the ordered pair, 0, -8. So like on the last one, I could have just divided by -1 or multiplied by -1 here, and got us to our answer. So graphing these 2 points, 2, 0 and 0, -8, and then connecting them. Let's move on to number 5 here. So if I start with either intercept, I'll just do the x. That's what I typically do to start. We'll do -5 times x minus 4 times 0 equals -24. -4 times 0 is 0, so I'll just go ahead and divide by -5 on these two parts. And I get x equals positive 24 over 5, which I prefer as a decimal when graphing to make it 4.8, and so that's 4.8, 0. Next, I'll do the y-intercept. So -5 times 0 minus 4y equals -24. And just like with the x-intercept when y just became 0, this will just become 0, so I can ignore that essentially because it at 0 minus 4y is just -4y. So dividing by -4, we get y equals 6, or 0, 6. So now I graph these 2 points, 4.8, 0, so 4.8 to the right, and 0, 6, so 6 up. Then I connect those 2 lines, and we have our graph. Next, on number 6 here, finding these intercepts, we've got some fractions here. X-intercept, we have 3/4 x minus 1/3 times 0 equals -2. Then we'll multiply by the reciprocal. 4/3 undo the 3/4. 4 and 4 reduce, 3 and 3 reduce, all become 1. And we get x equals, remember -1/3 times 0 is just 0, and we don't have to add or subtract 0. Put this -2 over 1 and multiply straight across and get -8 over 3. 2 and 3 did not reduce, so we just left it as is. This is the decimal. If you'd rather, -2.6 repeating, which is what I'm going to put it in as. Now let's go ahead and find the y-intercept by making x 0. So 3/4 times 0 minus 1/3 y equals -2. I multiply by 3 over 1, but a negative, because this is negative, and I do it to both sides of the equation. Just remember, this ends up becoming 0, so we don't have to deal with that. -3 and -3 reduce to 1 and 1, and we get y. Multiply this other side by -3 and get positive 6. If you wanted to put this over 1, that's fine. It doesn't really change it either way. So now we end up having 0, 6. So now I'll go ahead and plot these, -2.6, 0, 0, 6, and connect them. Moving on to our last problem, number 7. For the x-intercept, I'll make y 0, 5 over 2x plus 5 over 6 times 0 equals 6. This just becomes 0, so I can ignore that and multiply by the reciprocal of 5 over 2, which is 2 over 5. The 2's reduced to 1 and 1, 5's reduced to 1 and 1, and we get x, Over here, if I put 6 over 1, 6 and 5 do not reduce, so we multiply straight across and get 12 over 5, which is the same exact thing as 2.4. So I'm going to call it 2.4 comma 0 to make the graphing a little bit easier. Then over here, as I do the y-intercept, I make x 0, always the other variable that gets made 0. This all becomes 0, so I don't have to worry about it, and I multiply the reciprocal of 5 over 6, which is 6 over 5. 6 reduces to 1, 5 is reduced to 1 as well, and we get y. On the other side, as we multiply by 6 over 5, if I put 6 over 1 again, nothing reduces here, 6 and 5 do not reduce, and so I multiply straight across and get 36 over 5, which is the exact same thing as 7.2. So I'll call it 0, comma 7.2. Graph these 2 points, 2.4 comma 0, approximately there, 0 comma 7.2, approximately there, and I connect them. I'll try and connect it a little bit better. There we go. And that's my graph. And that